Okay, so general relativity for cosmology. We're going to study this fascinating view here of the universe. But first, let's talk about some logistics. So this course is offered both as an A-math course, but also as a physics course. It doesn't matter which way you sign up, it's the same deal. If you would like to sign up for credit, you'll make me very happy. If you sign up for just for audit, that's fine as well. If you would like to just come and visit and listen in occasionally, that's fine too. However, if you do come regularly, it would be great if you signed up at least for audit. But anyway, whichever way, you're always welcome. So our lecture times are Mondays and Fridays, 1:30 to 2:45 or to 3, something like that. There are a few exceptions, though. We're not always going to be in this room, and not always at that time. So here are the exceptions. I'm listing them here as they happen. Sometimes PI has to use that room for a conference, for example. Then we have to move to another room. Or there is a holiday coming up and then needs to be rescheduled. I'll keep all the information about that up to date on our homepage. Has everybody found that homepage? If you go to my homepage and then click on teaching, you will get that, that page. So in particular, this term is very short. It's shorter than usual because I think it was Labor Day was late or something, so normally we would have started about a week ago. So the university wants us to make up for the Thanksgiving Monday with another lecture another time. I'm very happy about that because we have a lot of material to cover. And so what I've arranged is that on Monday, okay, so Monday 12th of October is Thanksgiving, no class. However, we'll make up for that on November the 9th by doing a double lecture. Okay, so we'll just go on and on and on and on. But I'll make it, I hope, okay. I bring stuff from Tim Hortons and drinks and stuff so that we can survive a double lecture. So we'll go, you know, one lecture, then have a break, and then have another one right afterwards. The venue is generally here, this room, Alice room. But PI will have conferences and other events. I don't know exactly what is in the way, but the administration wants us to move our classes of September 28th and October 2nd to the Bob room, which is just one floor up. So please don't forget about those things so that you always know where and when things are happening. Office hours are by arrangement. Just let me know, and we'll set something up. Okay, so here I'm explaining, you know, what we'll cover in the course, but we'll go through that, of course, in a little while in more detail. In general, the way that the lecturing of this course works is that I will post lecture notes ahead of the lecture, and I will post the lecture notes on this homepage. This, for example, are the lecture notes of the previous offering of this course 2 years ago. I will update them. This term, I will add a little bit extra material, for example, on black holes, because recently I've been to a black hole conference and totally blown away by what they do. Did you know that there is this telescope coming online now, the Event Horizon Telescope? It's just fascinating. So we'll do a little bit more about that. So those lecture notes are not going to be exactly what we cover this term. The ones of this term I will post each week, I mean, a day or two before I actually teach it. Maybe even the night before I teach it. Okay, but it will be posted before class so that you can print it, and so you don't have to take notes while I teach it. You can just print it out and annotate it during the lecture. Or maybe just keep it online if you like. So I've already posted lecture 0, which is not going to be taught. It's just a review of the transition from special to general relativity. Please read that in your own time, but do read it. I mean, for most of you, this might be very simple stuff. it has, for example, a quick derivation of time dilation and so on. But also some general arguments for why we need GR and what is to be expected. All of that review. I mean, I'm hoping that almost all of you have done some GR before. But in any case, we are going to start from scratch, even though it'll be a little fast. And I've also posted lecture 1, which is what we'll cover today. So you just click on the underlined stuff. That's the PDF of the lecture notes. I'm hoping to get away with not posting a final, not putting a final exam. There's some dispute in our department about whether or not there should be a final exam. I hope we can all be adults about this and not have necessarily a final exam, because I think that's very much like undergrad stuff. So the plan is to have an essay and a project. The course will cover a lot of mathematical material, and then the physics, and then applications. The idea is that you write an essay about the material that is part of the first half of the course, mostly mathematical, and then a project where you actually get to hands-on calculate something, mostly numerical, some of it also analytical. We'll see about the second half of the course. So that on one hand, in the essay, you reflect on some of the conceptual issues and how you describe curvature, for example, and what are different methods for describing curvature. And in the second part, you hands-on try out some things to do with general relativity. Here, I just copied the essay and project descriptions of the last time I offered it. I will tweak those a little bit and update them, and we'll let you know when we have the actual version of the essay and the project. Right, and there's also, please scroll that far. Don't give up at that part there. Please scroll also this far to read about the general advice that I put up here on what is expected in essay writing, what is expected in making a project. And there's also some literature at the end that you may want to look into. Much of it is freely available electronically. Okay, any questions so far? If not, then let's close this. Open that. All right. Okay, so lecture 1. What do we see here? This is the so-called tadpole galaxy. But let's not be completely distracted by that beautiful galaxy here. Actually, it's the product of a collision. A smaller galaxy ran into it, and this is like the a trail left by the collision. This galaxy is about 420 million light years away. But I'd like to point your attention to those little specks here. Those things are also galaxies. And galaxies come in different sizes, but roughly there's an average size. And clearly, since this one is 420 million light years away, those little ones are not really smaller, they're just further away. And you can see in this image already almost halfway through the universe, or perhaps even further. Not just, spatially you can't, it's temporally. It may well be that the universe is infinite in spatial extent. We don't know that. We have no way of knowing that at the moment. But in time, we are looking back, in this case, 420 million years. And so what we see here is billions of light years old. This light is billions of light years old, which is a significant fraction of the total age of the universe, which is now estimated to be 13.8 billion years. I find it quite dramatic. It's almost claustrophobic, right? That you can actually see the whole thing. Now, what you can't see on that picture very well, but on this picture is GR in action. In this picture, you see Einstein rings, so we see the curvature of space-time quite directly namely through its lensing effect. So clearly Newtonian gravity is not going to do it. Space-time is really curved. But how do we describe space-time? So this is what this course is going to be about, how to describe space-time. And I will have several aims in this course. One is, of course, to present the math needed for general relativity, and then general relativity itself, and then applications. But the point is to prepare you for work in quantum gravity, in black hole physics, or in cosmology. And especially in quantum gravity and cosmology, well, and also in black hole physics, quantum effects are going to be important, crucial. And as you all know, it's proven extremely difficult to come up with a theory that unifies general relativity and quantum theory. Part of the reason for that is that they are mathematically formulated in two very different languages. General relativity is formulated in the language of differential geometry, and quantum theory in the language of functional analysis. There's very little overlap mathematically between those two. And so whenever we now start developing the differential geometry, just always keep in mind, it doesn't have to be like that. It could be that there are some idealizations and assumptions that went into the formulation of differential geometry that were intuitive at the time, but may not match nature. See, there are two notions of truth at work here. You can view truth as a mathematician as what you can derive from axioms. But you can also view as a physicist truth as what matches observation. And those two are independent notions of truth. You can very well have mathematics that's consistent and true in the mathematical sense, but is an over-idealization and just doesn't describe nature. Vice versa, you can also have mathematical formulations that describe nature. I'm thinking of the path integral in quantum field theory, for example, that do describe nature with high accuracy, so they're true in that sense, but they're mathematically inconsistent. We know that there is something up. It's not clean mathematically. It's not true mathematically speaking. Now, some people subscribe then only to one camp or the other. They become mathematicians and buy into over-idealizations at the benefit of being completely true in the mathematical sense, but it's not true in the physical sense. And others would say, no, math is just too tedious, and they would go and become pure physicists and say, well, whatever works. But then they run the risk of getting into contradictions. I think we should not decide on which camp we want to be in, but rather live with that tension between the two. That's probably the most creative way to work. And so this course is not going to be pure mathematics. It's also not going to have the attitude of whatever works. We're trying to, be true and correct. Have it mathematically right, but also physically right. But on the other hand, we can't go too deep into the experimental evidence or into the axioms and in the pure mathy way. So it will be in the middle between the two. And let's always keep that dichotomy in mind. So how do we describe then space-time? Well, there's the math part of it. And actually, I can make that screen bigger. Getting rid of this stuff. Oh, I know. Yep. Okay. So we start with the math of it, how to describe space-time. And if you think about it, what we will do now, what I've described now, is older than general relativity, and crucially, it is older than quantum theory. So let us always keep that in mind. We start, in order to define differential geometry, we start with a mere set of points that we will call events. A point in space-time is an event, right? A location in space and a location in time. That is an event. And the set of all those events we will call M, a manifold. That's how we would describe space-time. It's primarily a set of events. It's not even clear that that is physically the right thing to do. But let's just start with a set, and then we add more and more structure to it. In particular, we will have to add structure so that we can make sense of notions such as continuity and such as differentiability. Because that's just such useful notions, we need to prepare the ground to define that and to check, do we have continuity, do we have differentiability? We need to know what do we mean by that mathematically. Now, in order to define continuity, we will first need another notion, and that is the notion of open sets. So we will define open neighborhoods of those events. And if they obey certain conditions, certain axioms, we will call this a topology on this set of events. We will also define the notion of separability of points. The notion that they don't sit on top of each other, there's always some space in between them. That will be a so-called Hausdorff condition. Having these, we can then define, especially topology, we can then define the notion of continuity. It turns out that continuity can be defined in terms of open sets. The pre-image of every open set is an open set. That's the definition of continuity. So this prepares us for defining what we mean by continuity. And then the next challenge is to define differentiability of such a set of points. And we will do that by mapping the problem to a known problem with its known solution. And that is differentiability on Rn. We all know how to define differentiability on Rn. If we can somehow map the problem of differentiability that we face here for a manifold to the problem of differentiability on Rn, then we're in good shape, because we know how to do that. And that's the strategy that we will pursue here. Later then we can define tangent and cotangent and tensor spaces, and then we are in business and we can develop differential geometry. Just like to remind you again that, this is pre-quantum. We don't know whether this is going to survive to the theory of quantum gravity, but it's standard differential geometry. This is how general relativity is defined, and we will follow that path. So once we have a definition then of tangent spaces, tensor spaces, and so on, we can then define curvature. And you probably already know that curvature can be understood as the non-triviality of parallel transport. If you parallel transport a vector along a parallelogram on a curved manifold, then when you return to your starting point, the vector that you parallel transported no longer points in the same direction, generally, as the direction in which it pointed when you started the trip. This is one way to define curvature, and it's a standard way to define curvature for the purposes of general relativity. But it's far from being the only way to do it. And again, since most of the applications of general relativity today involve quantum theory in one way or the other, quantum black holes, quantum cosmology, let us consider also that there are other ways to describe curvature. For example, curvature can also be understood as the fact or the phenomenon that the sum of angles in a triangle doesn't have to be 180 degrees. It could be different, and that is a sign of the presence of curvature. There are theories of quantum gravity that are built on that observation, rather than non-triviality of parallel transport. Curvature also modifies Pythagoras' laws. So when Pythagoras doesn't hold, it's an indication of the presence of curvature. Gauss even did experiments on that. Well, of course, curvature of space-time is far too small to have been measured more than 100 years ago. But the idea was around for those checks whether space-time is really curved or flat. Curvature can also be understood as the presence of tidal forces. You all know that when a body is freely falling, then it is just like as if it were in inertial motion. I mean, you can't completely locally, you can't tell, whether you're freely falling or not. However, that's not quite true. If the object that's freely falling is extended in size, then part of it may be freely falling one way, and the other part, a little bit further away, may be freely falling another way. In fact, if the moon were, for example, to get much closer to the Earth, then the orbital frequency of the part of the moon that's closer to us, would be a different orbital frequency than the orbital frequency of the part of the moon that's further away from us. That would rip apart the moon. And these are tidal forces. So curvature can also be understood as the presence of tidal forces, when the motion of free fall is different here from there. If two parallel traveling observers, two parallel traveling freely falling astronauts go separate ways, that's tidal forces, and the mass of that is the mass of sectional curvatures. It's another way of expressing curvature that's identical, equivalent, not identical, but equivalent to the others. Curvature can also be viewed in yet a different way. This is something that I've been working on myself. Curvature can also be viewed as the non-triviality of the sound that an object makes. Take, for example, a vase with some shape. Let's assume it's empty. Let's say you take a spoon to it and make it ring. That vase will have a certain sound, a certain spectrum. The spectrum is a function only of the shape of the vase. The actual amplitude of the various overtones depends on how hard you hit it and where you hit it with the spoon. But the frequencies don't depend on that. The frequencies only depend on the shape. If you take a vase with a different shape, it'll have different frequencies. So what you see here is that the curvature corresponds to spectra. There's a discipline called spectral geometry which studies to what extent the shape of a manifold is determined by the spectra of certain differential operators on that manifold. In the case of a vibrating vase, it's the Laplace operator on the vase, which enters into the wave equation. Its spectrum is the spectrum that you hear. I find that way of expressing or working with curvature particularly fascinating because it is intrinsically linking the mass of GR, general relativity, to the mass of quantum theory. See, on one hand, we have curvature described by differential geometry. It's the shape of things. On the other hand, we have this spectrum of an operator, which is intrinsically a functional analytic notion. It's something that quantum physics is familiar with. And the ultimate idea in that approach is that you could do that for space-time. Space-time itself has a shape. Space-time itself has curvature, much like the vase. Now, what's the spoon, though? Am I saying that you have to take a spoon now and bang it on space-time to make it ring, and then listen how it sounds, and then from the sound you can tell what the curvature was? Well, almost, except you don't need a spoon. Because space-time is always ringing. Because of quantum fluctuations, you can assume that space-time is always ringing. Not that we can measure those fluctuations of space-time itself, but we can measure fluctuations of quantum fields that live on space-time. And if space-time's curvature is changing, the sound of those quantum fluctuations, if you can measure them, the sound will change. And you can ask, to what extent does the sound of the quantum fluctuations, the spectrum, the correlator, to what extent does that describe the curvature on the space-time? And there you have a link then between the math of the differential geometry, the math of general relativity, and the math of quantum theory, which is all about quantum fluctuations. In fact, you can go a step further, because quantum fluctuations have, the quantum noise that you have on a space-time is correlated. It's a very important property of that quantum noise, and that correlation is due to entanglement. And so ultimately, you can try to describe the curvature of space-time in terms of the entanglement of the vacuum state. Anyway, this is not, I mean, we're not going to get this far in this course, but I will teach next term quantum field theory for cosmology, and there we will address points like that. So this course is a preparation, but it's going to be almost 100% classical physics, not quantum. Here are some papers that you can look up if you want on the issue of spectral geometry and how shape can determine, can be determined and determine spectra. Okay, so point A was the math, was how to describe a manifold, how to describe curvature, and point B now is what we will do when we study general relativity. So when we apply all of this math to the study of general relativity. So on one hand, we'll of course study the equations of motion for scalars, for vectors, for spinors, and for curvature itself. We study the symmetries of space-time and the corresponding local and global conservation laws. Keep in mind that, oh, they're looking for the washrooms, they're not there. Everybody clear that there's no energy conservation. Right? General relativity tells us there's no energy conservation, neither momentum nor angular momentum. There are approximate laws, and there are exact laws when there are high symmetries. But of course, space-time itself, actually, as it actually is, it doesn't have any symmetries and no exact conservation laws. So we will study that, and what can be done about it. Approximate conservation laws. I mean, for example, you have galaxies that smash into each other. It would be great if we could talk about the kinetic energy that they have before they crash into each other, the potential energy, and then work out what happens there. And there are approximate notions that are very useful for that purpose. We will study the tetrad formulation of general relativity, which is also a way to write general relativity as a gauge theory. Here, roughly speaking, the idea is this. Remember in quantum mechanics that you can write down the Schrödinger equation in the position representation. You can also write it down in the momentum representation. And there are many other representations of the same theory. They are all just choices of bases. And the physics is independent of whatever choice of bases a human makes. In general relativity, the same thing is true. We have a choice of coordinate system, and the physics surely will not depend on the choices of coordinate system that we make. But there's more. In the tangent and cotangent and tensor spaces, we have a choice of bases. And again, which choice of bases we make cannot possibly affect the physics. But then if you've taken a first course in general relativity, chances are that for simplicity, in that course, whenever you chose coordinate system, you also automatically induced a choice of bases in the tangent and cotangent spaces. There's no need to do that. There's no need to change the bases in the tangent and cotangent tensor spaces along with the change of coordinates. It's independent things. Choice of coordinate is one thing, choice of bases in the tangent space is another thing. There is a canonical way to adjust the bases along with the coordinate system, but it's just convenient for certain simple calculations, but it's not fundamentally important. With the tetrad formulation, we free ourselves from that and we choose them independently. And in particular, you may want to not choose to change the bases in the tangent space just because you change coordinates. What that means is profound. It means that what you were told earlier, namely that a vector is what transforms like a vector, is no longer true. A vector is not going to change, a tangent vector is not going to change its components at all if you change coordinates. It's only changing its components if you change the basis in the vector space in which it lives. And you don't have to do that along with the change of coordinates. So this will give us a lot more freedom, and we will then see more clearly what is really going on in general relativity, because we are doing things in a more basis-independent way. Just like in quantum mechanics, it's worthwhile doing things basis-independently. In general relativity, it is as well. But then we will study singularities and theorems that show that under certain circumstances it's unavoidable that singularities will form, such as the singularity in a black hole, or the singularity at the beginning of the universe, or even the end of it. And then we will work on applications to cosmology and also black holes. We will study exact solutions that are known for general relativity, which is, they are a big deal because general relativity's equations of motion are nonlinear. And so it's really difficult to find solutions. We should appreciate every one we have, can learn from them. There's a classification of exact solutions. We will study models of cosmological matter. We will study the evolution of space-time and the cosmologies that they describe. We will describe again Friedman-Robertson-Walker models of cosmology, but now using the tetrad formalism. In this way, we get to the solutions much quicker. But also it's conceptually cleaner because we describe things in a basis-independent way. And so this is a way to exercise the methods that we developed. Also for black holes, we can use the tetrad formalism to quickly get at solutions. And then we will study the standard model of cosmology today, which is cosmic inflation, well, the classical part of it, which provides an explanation for why space-time is, to such an incredible accuracy, flat, for example. See, on large scales, the universe could be curved, but as far as we know, it's completely flat. There's no evidence pointing in another direction. It's spatially flat on average. Yeah, and then we will also study black holes to some extent. Okay, so this was the overview. Let me see, when did we start at 1:30? Yeah, great. Okay, so this was the overview. Any questions so far? Because if not, then we just start with the math. Has the information sheet gone around to everybody now? And also the lecture notes, does everybody have a look into it? Okay. Yeah, I don't need it now, just later, thanks. Okay. All right. So let's begin then. So we will study Riemannian and pseudo-Riemannian differential geometry. Riemannian meaning just space, and roughly speaking, and pseudo-Riemannian meaning space and time. So it's either Euclidean metric or metric with a Lorentzian signature. So the notion of differentiable manifold has a long history, and it goes back to Riemann and then Poincaré and Whitney and some others. The point I want to make with that list is that it starts very early, 1850. I mean, compared to GR, compared to quantum theory, it was early. And the first definition here is that an n-dimensional topological manifold is a Hausdorff space which is locally homeomorphic to Rn. So I will not assume that you know all those terms. Let's define them now. So a topological space is a set together with a specification of subsets, Ui, which we will call open subsets. And they must obey that the intersection of any two such open subsets is, again, an element of the set of declared open subsets. And also any arbitrary union of open subsets is open. Remember what this is about. Why do we do this at all? We start out with describing space-time as being a set made out of elements that we call events. And the first notion that we want to encode is continuity. Now there is an abstract definition of continuity that reduces to the usual delta epsilon definition of continuity of ordinary calculus, but which is much more general. And that abstract definition of continuity is that if you have a map from a topological space into a topological space, a space with open sets defined in this way, and the pre-image of every open set is an open set, then this is a continuous, and this is a continuous map. So again, a topological space M is a set, in our case, of events of space-time, and together with that specification of the events, we also have to give a set of subsets, Ui, which we will call the open subsets, and we can't just choose them arbitrarily. They must be chosen in such a way that the intersection of any two of them is open again, and that means also any countable number of them is open, and also any union of open sets is open again. Next, we want to encode the idea that if X is an event and Y is an event, then there ought to exist an open set around the first event and an open set around the second event. Let's call the first open set Ux and the second set Uy, such that they don't have an overlap. This means that X and Y are separable, distinguishable. If for any 2 points of the manifold there are, which are not identical, there are such subsets which don't overlap but contain X and Y respectively, then we say that the Hausdorff condition is fulfilled. And the mathematical way to write this is, I would sometimes use those symbols. So just to make sure every one of you has seen them, this upside down A means for all. So for all X and Y, for which it is true that X is not equal to Y, there exists. This is the left-right inverted E symbol, means exists. Two open sets Ux and Uy, such that X is contained in Ux, Y is contained in Uy, and the intersection is empty. So there is some space in between. So our space-time, our model for the space-time now consists of all those events together with the specification of open sets. Remember that Rn has that anyway. Rn is a set of points for which you can immediately tell these are open subsets. So Rn clearly is a topological Hausdorff space in the sense that we just defined above. And M is by assumption or by construction. So now we have two of those topological spaces. And then we can define what we mean by continuity. Remember that if A and B are topological spaces, so they are sets with a notion of open subsets, then a map that goes from A to B is called continuous if, let me just put it in words, if the pre-image of every open set is open. So if you have that V is in A and U is the image of V, then when U is open, V is open as well. If you do that for maps from R to R, this recovers the usual definition with deltas and epsilons of continuity. But it doesn't rely on a notion of distance. This makes it more powerful. So now we have the ability to express the idea that M is continuous in the sense that its events are continuously parametrizable. So M is called locally homeomorphic to Rn, which it stems from the Greek, means equal structure. So M is locally of a similar structure to Rn, in the sense, what we mean by that is continuous. If at each point P there is a neighborhood, U of P, and there is an invertible continuous map from the neighborhood of our event, into Rn. I'm really talking about the coordinate system here. Okay? So every point P has a neighborhood around it, such that there is a map from H, from that neighborhood of the event into Rn, which is continuous with regards to the topology on Rn and the topology on our manifold. To a physicist, all of this sounds a little contrived, perhaps, because, you know, how do we actually write down all those open sets, for example? And in any case, nobody's ever pinned down an exact event in a space-time. But don't blame the mathematicians. The thing is that this notion is very powerful because the notion of manifold has been invented not just to describe space-time. You can have a manifold of differential equations. You can have a manifold of many different mathematical objects. And they may very well obey exactly those axioms. This might be just exactly the right thing to describe that, and often it is. But let's keep in the back of our mind that it's not obvious that this would describe space-time. But it's the standard way. Just let's keep a question mark along with it. As far as the physics is concerned, as far as the math is concerned, it's fine. But the physics we'll have to reconsider sometimes. Okay, so such a local homomorphism, such a continuous map from some domain in the manifold into Rn is called a chart of M. So if you have a continuous map here from some patch of the manifold into some patch of Rn, then that is called a chart. It's a continuous parametrization of the event. Every event is then described by a point in Rn. A point in Rn is described by n numbers, n real numbers. So we have, through this continuous map from the patch of the manifold into Rn, we have that every point Q in that patch is mapped into H of Q, the image, which is an element of Rn, which is n numbers. Let's say call them x1 to xn, and so this is then the continuous parametrization of the points, of the events of the manifold. And they are called, of course, the coordinates of that point. So the overall structure is that here we have the manifold. Here we have a patch in the manifold. The manifold has a topology, so does Rn. Generally, I will depict the manifold as something wavy, curvy, and Rn as something with right angles for no good reason, just to keep them really apart from each other. So we have the manifold, we consider a patch of it, and then we consider a continuous map. Now we know what continuous means. It's with respect to the open sets here and the open sets there. Every pre-image of an open set here is an open set over there. Any such chart is also called a local coordinate system for that patch. Now, two issues. What if we want to change chart? What's the math of changing chart? Changing coordinate system. And the other issue is, and that seems like a mere technical issue, and we will address it, it's pretty straightforward. And the other issue is, we have continuity now. How about differentiability? What do we need for that? It turns out we can combine the two. Change of chart and our desire to define differentiability. We can use the one for the other. Let's define a collection of charts, so a collection of coordinate systems. So we are now going to deal with several coordinate systems and the changes of coordinate systems. Let us consider let us call a collection of charts. Oh, by the way, when I write def, it just means definition. Okay, it's a long word, and if I wrote definition, then it would go up to here, and it would make the page smaller. So, okay. Also, differentiability in my writing sometimes becomes diffability. That's just to abbreviate it. Okay, so a collection of charts, H alpha, on patches U alpha, or really domains, that's the proper term for them, is called an atlas if, well, just like an atlas of the Earth, it's supposed to cover all of it. So if the union of all those patches, if the union of all those domains is the manifold. So what if we want to change now coordinates? So we want to relabel the points on a subset of the manifold. So consider two charts, H1 and H2. And H1 is mapping this domain, that patch, into Rn. And H2 is mapping continuously this patch, this domain, U2, into Rn. I could have made that the same, they are isomorphic, but maybe it's clearer to write it in this way. Now, all the events in here, all the points in here, have two sets of coordinates. We can either view them through this chart as having coordinates according to the map H1, but they also have coordinates according to the map H2. Every point here is described by, has an image, which is n points, namely the components of a vector in Rn. But it also has, the same point also has an n-component vector description in Rn through H2. What if we want to change coordinates? What if we know the n-coordinates of a point in here, and we want to know what the n-coordinates of that same point are in that coordinate system? Well, then all we have to do is just invert that map, and then map forward in this way. So H1 inverse maps from here to there, and then H2 maps from there to here. If we concatenate them, that's described by this little circle here, so we first perform the inverse of H1, and then append H2, then this is, because that is continuous and this is continuous, the whole thing is continuous. So we get that the map H index 1, 2, which is this total map here, is a map from a subset of Rn into a subset of Rn, which is continuous. So that's a change of coordinates. Maybe not such a big deal, but consider that for a map from Rn to Rn, we not only know what makes it continuous, we can also check whether or not such a map is differentiable. So we now have a handle on differentiability. We can say, aha, there are changes of coordinates which are differentiable, and there are changes of coordinates which are not. Right? So for maps from Rn into Rn, we know what differentiability means. So the idea is, let us define the differentiability of an atlas, which is, a bunch of coordinate systems which together cover the entire manifold, through the differentiability of its chart changes, of its coordinate changes. So an atlas is called CR differentiable if all its coordinate changes, H alpha beta, are CR diffeomorphisms, which is to say that they're all R times continuous differentiable. But an atlas may be very sparse. For example, an atlas of the Earth may contain only like 3 maps. Those maps might, one map might cover all of the Pacific and the Americas. And then another map covers the Northern Hemisphere. Another one covers the Southern Hemisphere. The whole thing covers the Earth. But you can have situations where some events, some points of the manifold are contained only in one chart. So you don't even really have a change of chart for that point. The atlas is not big enough for that. So you're not covering then the notion of differentiability for that point. If a point is only contained in one coordinate system, but not in the others. So therefore the idea is to enlarge a given atlas so that every point in the manifold, so that every event is in multiple charts. In fact, in as many as possible. then the differentiability of the manifold itself can then be defined through the differentiability of its atlas. So for that purpose, we extend atlases. So assume given a CR differentiable atlas, let's call it A, we can then use it to generate a maximal CR differentiable atlas, let's call it D of A, by adding all charts whose charge changes with charts in the original atlas are differentiable. So you can imagine if you have an atlas of the Earth, you can make that much bigger by cutting each map into smaller pieces and so on. As you get lots of patches, patch maps, it's a huge atlas. Then it has, of course, infinitely many charts and infinitely many chart changes. And in particular, every point in the manifold will be contained in many, in fact, infinitely many charts. Then this maximal atlas, it's actually unique, is called a differentiable structure of class CR for the manifold in question. Now, a differentiable manifold of class CR is a topological manifold with a maximal atlas of class CR, that is to say, with a differentiable structure of class CR. So we are saying that if the manifold admits that, I mean, if we have a manifold and we have an atlas which has this differentiability, we make it maximal, and then if the maximal atlas has this property of being R times continuous differentiable, then we say that the manifold itself is a CR differentiable manifold. Now you might think that this is similar to functions. Functions can be continuous, and sometimes they are better than that. Sometimes they are differentiable. Sometimes they are 5 times differentiable. Some functions are infinitely many times differentiable, in which case we would call them smooth. And you might think that with manifolds it's probably the same. There will be manifolds that are continuous, but can't give them a differentiable structure. And some manifolds might be R times differentiable, but not R plus 1 times differentiable. It turns out it's not like that with manifolds. There's a theorem by Whitney which shows that every CK structure with K larger equal 1, so whenever you have differentiability at least once, then CK is equivalent, then this structure is CK equivalent to a C infinity structure. Or another way to say it is that if you have a CK manifold and you have that its coordinate charts are K times differentiable, continuous differentiable, but not K plus 1 times, then you screwed up with your choice of charts. Because there is another choice of charts that is better, that has better differentiability. If you have differentiability at all, you can always find charts such that it's infinitely differentiable. It's not guaranteed if your manifold is just continuous, but if it is once differentiable, it's as many times differentiable as you want. And that means that when we speak of a differentiable manifold, we might as well speak of a smooth manifold. And so that's what we will do. Of course, we will speak of smooth manifolds then. Yeah, that was the last definition. So any C1 manifold is also C infinity manifold. So we call differentiable manifolds simply also smooth manifolds. All right, this is all of the material that I had planned for today. We have plenty of time left, actually. If you have any questions, do ask.
So when we talk about later on, we're going to talk about the gauge groups and stuff like that. We're going to talk about the gauge group with related to, I guess, first the electromagnetism, which is E1, and then we're going to go into like the gauge group on manifold, right? Spiro said that the gauge group is just a collection of all the collections of the group of diffeomorphisms. Is that what it is?
No, actually, if you remember what I said earlier about the freedom to choose bases in the tangent and cotangent spaces.
Yeah.
Now, if you go from one basis to another basis, you can do that with the local Lorentz transformation. And it's essentially local Lorentz transformations that are the gauge principle of GR. You can even make it local Poincare transformations in a certain sense.
Okay. That makes sense.
Yeah. But I have an idea. Oh, yeah, okay. Go ahead. No, my idea was that maybe if you have a few questions, I'll answer those questions, but also we could just go around and everybody just briefly says who they are and how far you are in your studies so that the group gets to know each other a bit.
Sure.
But go ahead.
I just wanted to ask, when you define manifold, you define like the open sets as well. Can you define like closed or compact manifolds with that?
Yeah, sure. That's how it's defined. Yeah.
How would you do like? Because you say like the union of all the U's has to give your manifold, right? But the union of your U's is always going to be an open set. Sure. But
yeah.
Always going to be the case.
And the whole set is always both open and closed?
Yeah.
By defining open sets, you define closed.
Right.
Yes. The thing is, we are not going to use these definitions very much when we go on from here. We will pretty quickly move on to define the tensor spaces and then on to affine connections and curvatures and so on. And so we will not have much time, unfortunately, to look into differentiable manifolds on their own. But maybe I should make that a particular point here clear, which is that with these definitions, we obtain what is called a differentiable manifold. And you may have in your mind a picture of a differentiable manifold as having some sort of shape. It might be a sphere, or it might be an ellipsoid, or maybe a torus, or something higher dimensional, and so on. Technically speaking, it is none of that. It cannot have a shape, because we have not defined a notion of distance just yet. Remember that you can get topologies, you can define open sets if you have a notion of distance, such you have on like on Rn, distance between two numbers is the absolute value of the difference, for example, then you can use that to define open sets. But you can define open sets without having a notion of distance. And that's what we've done so far. We've not relied on a notion of distance. There is no definition of what the distance is between 2 points. So all we really know about a manifold at this point is what we specifically specified. And that is how things hang together. That somehow, 2 points, if they're different, they can't sit on top of each other. That was the Hausdorff condition. And also, we have specified that the points can be continuously labeled. And the relabeling could be at least continuous or maybe differentiable. But none of this implies any knowledge of how far apart 2 points are. If you take 2 events and you consider their coordinate distance, let's say one coordinate vector has very different entries from the coordinate vector of another point, it doesn't mean that those 2 points are very far apart, because you can relabel. You can find a coordinate system in which the 2 points will have very, very similar coordinates. Just stretch things or compress the coordinate system, and you can make any 2 points seem very close to each other or very far from each other. Of course, all in a differentiable or continuous way. But there is really no notion of distance, and without a notion of distance, we have no notion of curvature, we have no notion of shape. These things, those manifolds still don't have any shape whatsoever. If you have open sets, you have very, very little. And it will require extra definitions, extra structure, to endow those manifolds with what might be thought of as shape. So intuition is still very limited at this point. It's just the groundwork for what manifolds might be then.
But then,
every manifold is locally homeomorphic to R, and R itself is a metric.
Yes, that's right. But that's right. And in principle, what we could do is we could pull that back onto the manifold and say Rn has distances, Rn has curvature. In fact, it's 0, but it has a definition of curvature, and that is 0. And we could pull all of that back to the manifold, in which case it would be just Rn again. It would be flat. So we don't want to do that. We want to use the chart to get a handle on differentiability, but we don't want to borrow too much from Rn. So we will add extra structure to the manifolds, which then allows us to have it describe shapes, actual shapes. Yeah?
So I imagine this subtlety will come up that much during this class, but like, so you mentioned it again, right? It's like any C1 manifold is also C-infinity, but just a few lines back, we talked about how there exists a chart that will have C-infinity.
Mm-hmm.
Not necessarily the chart you initially choose. So how often does that kind of the initial chart you choose has only CR differential structure and the results of all this?
Well, in this, I don't know of any example in physics where that would come up, where that particular thing would come up. But you probably all know that there is a similar issue arising with the Schwarzschild solution of black holes and the Schwarzschild coordinates. The Schwarzschild coordinates provide a chart, but in that chart, it looks as if there were a singularity at the horizon. And Einstein and others at first thought that this is really a singularity. But it's not. It's just an unlucky choice of coordinates. And that can be smoothened. You can choose Kruskal coordinates or others, and then you notice that at the horizon, there is really no singularity. There are funny things happening, but it's not singular. So it's similar in the sense that it smoothens. In fact, it actually smoothens in the sense of, it's more dramatic because it removes what looks like a singularity. And similarly, you could have a choice of coordinate systems that is continuous but not differentiable, but you can fix that with a better choice of coordinates. Yeah. I mean, you can always, on purpose, cook that up. I'm just saying that it doesn't seem to naturally come up in physics. Yep.
So this phenomenon is that so CK structure is maximum atlas is right?
Yeah.
So that means when we choose different set of atlases to begin with to build a maximum atlas, we can go higher and higher in terms of
okay, yeah.
Right?
Mm-hmm.
Does that mean that CK is within CK plus 1 or?
Yeah, sure, yeah. I mean, you can go from CK to CK plus 1 to CK plus 2 all the way to C infinity. Yes, but I should say that I'm not an expert in that, but it turns out that when you are given a differentiable when you're given a topological manifold, then you may be able to give it different differentiable structures, and there is a hierarchy happening. Let me put it this way. Imagine we take, let's say we take a differentiable manifold, and then we add structure. This doesn't have shape yet, and then we add structure to it, maybe a metric or a connection, and then it acquires shape. So for example, we could start out with a differentiable manifold which is topologically the same as a sphere. And then we give it some shape, so then it becomes really a sphere, or it becomes an ellipsoid, or so on. But you can give it different metrics. You can put different connections on that same differentiable manifold, and then it acquires different shapes. And similarly, you could start on a more basic level with a topological manifold and add this differentiable structure or another differentiable structure to it, and you get different outcomes in these cases.
So we do already have a notion of whether it's a torus or a sphere.
Yes, sorry, I meant to send that. I meant to say that earlier. That's right. So on one hand, these differentiable manifolds or continuous or differentiable manifolds do not yet have a shape in the sense that they look like a duck or they look like an elephant or something like that. There's no notion of them having a dent or a bulge or something like that. However, they do have a notion of having holes and handles. And that's because of the continuity of it. Can't continuously turn what has a hole into something that doesn't, or has multiple of them. And so you can then, you can classify those differentiable manifolds with regard to their overall topology, which is like how many holes, how many handles does it have. It's intuitive. In higher dimensions, it's more complicated than having holes and handles, but it's similar. So any you can form those equivalence classes and ask, what is the structure of the set of those equivalence classes? You find the equivalence classes differential manifolds that have one hole and in 2 dimensions, others have 2 holes, 3 holes, and so on. And we will later in this course talk about that a little bit. It's on one hand, it's a big topic in math. It's important for things like string theory, but other than that, this global topology of how many holes and handles a manifold has does not really come up in cosmology. It might come up. There have been studies that investigated the possibility that the universe might have a non-trivial overall topological structure, and that might show somehow the cosmological spectrum. But there's no evidence that suggests that our actual universe is anything else than trivial topological. It seems to be just as a differential manifold as well as our core. I don't have any hope in it. The mathematical discipline that then studies those equivalence classes of differential manifolds. So that looks not at curvature at all, but just looks at how many holes and handles a manifold might have. That would be homology theory. And we will briefly cover that and look at what is Dirac homology, what is K-theory, and just to let you know roughly what these fields are.
Do we need a notion of metric to talk about orientability?
No, I think that's separate. Yes. Okay. And you could have, for example, in our universe, imagine you're communicating with extraterrestrials. You found some communication channel, but you can't travel there. And then you receive a message from them, and they inquire, so, majority of you, are you right-handers or left-handers? Then you might ask, well, what do you mean by right? What do you mean by left? You have to translate that anyway, right? So how do you tell them what is right, what is left? If you want to tell them that our heart's on the left side, how do you explain that? How do you radio that to them? And it is perfectly conceivable that you have a space-time described by a two-Riemann manifold with a metric on it, and physics as we know it, and there is no way of telling the other party what you mean by left. In practice, it turns out nature does distinguish left and right. The weak interaction works differently left and right. For example, the parity symmetry is violated, so there is a way to explain it. To explain it to extraterrestrials, you could say, remember the weak interaction? You know what it does? The neutrinos come out left-handed and so on, right? And then they will say, oh yeah, I see, that's what you mean by left. Right? But it's not contained in the notion of metric.
Just getting back to your spectral geometry, I was wondering, you made an example or metaphor of hitting a base and hitting with a spoon, right? Then that in terms of manifold, are we talking about like manifold with boundary conditions? Because when we think of a base and hitting with a spoon, that and seeing the spectrum of the base, then we are talking about the boundary condition, shape of wave, right? But then in your research, you were having a manifold with boundary condition, but in terms of relativity, we don't.
This is a very good question, and I should have clarified that. The spectrum of the vase will depend on both the shape of the vase and also the boundary conditions that the top rim of it will obey. In general, in spectral geometry, you can try to hear both. You can try to hear the shape, curvature, and you can try to hear what kind of boundary conditions you might have if there's a boundary. For example, you can try to hear, deduce from the spectrum whether you have dropping boundary conditions with some parameter or Dirichlet or Neumann boundary conditions. And in practice, you can't do both. You certainly can't do both the boundary condition and the curvature. But there are, if you focus on just the curvature, you have a chance of hearing the curvature. If you focus on just the boundary conditions, there's a chance of hearing just them. You can't hear both. There is a nice connection between the two through Stokes' theorem that relates what's going on the boundaries to what's going on in the drive. But generally, these are two different questions, and what I had in mind earlier was really a manifold without boundaries, such as space-time, which, by probability, doesn't really have boundaries. Maybe I should say too, just to give you an indication of what the spectral geometry business is about. The spectral geometry is very old, older than quantum mechanics, older than general relativity. Hermann Weyl came up with the idea in, I think, 1904. And ever since, mathematicians have studied, to what extent does the spectrum tell us about the shape, or tell us about the and it has been very tough going because it's a very nonlinear problem to calculate the sound from the shape. And then to calculate the shape from the sound is inverting a very highly nonlinear problem. It's very difficult. You can do it only in the presence of very high symmetry, but then it's no longer the generic case. And we're talking about a very special case. It's very hard to get a handle on the generic case. So what in my research I did is I said, well, if it's too hard, then let's apply derivation theory. Mathematicians don't usually do it. They either prove, disprove, or don't do anything. But derivation theory is something that, as a mathematical physicist, it's our main tool, right? So the idea then is to solve a more modest problem. Instead of trying to get the shape from the sound completely from scratch, just give me the sound, calculate the shape, it's too hard. Instead of that, assume that you know the shape and you know the sound both. But then somebody perturbs the shape a little bit, and that perturbs the sound a little bit. Now, the more modest question is, can you calculate from the change of sound what the change of shape was? It's much easier because it's a linear problem. See, if the change of shape was small enough, the change of sound would be small enough, it's a linear problem. You're calculating the tangent to this nonlinear map. And then you only have to check whether that linear map is inverted, but that boils down to a matrix or to an operator, a linear operator. And you can ask, is that invertible? And then you can make progress. And once you can do that, you can iterate. You can iterate this and get from small changes of sound to, build up the larger and larger changes in shape, and then you can solve the original problem. It's a bit like Riemann integration, I suppose. It's hard to get the area under the curve, but if you chop it up into tiny slices, then you're just having rectangles with a very good approximation. That's just linear stuff. And so similarly, you can try to integrate vector geometry from small steps. Actually, I gave a talk on this very subject right here 2 days ago. That was in the Alice room. There was a little conference, a workshop on non-commutative and spectral geometry, and so if you go to Pearsall and type in my name, then probably the top hit will be this particular lecture, but the second one will be, the second newest lecture will be the one that I gave on Saturday. And it was about the spectral geometry and that iterative process and how all of that might fit into quantum gravity.
You said you can't hear both sound from boundary and the manifold, right? You can't hear them at both.
Yeah.
I'm assuming by hearing, in terms of physics, you can't observe the fluctuation. Is that what you mean?
What I meant is that if you know just the sound, it doesn't completely even determine what the shape is.
Okay, so when you observe something but it has no meaning, is that?
Yeah, it has not enough meaning. So basically the spectrum, in general, the spectrum of a manifold will not tell you everything about its shape. It will not tell you everything about the metric. And what I showed in my work is that it's no wonder. And that's because by spectrum we usually mean the spectrum of scalar waves. The spectrum of scalar vibrations on the manifold. And curvature is not scalar. Curvature is tensorial. Which means that what we really should be listening for is the sound of scalar, vector, and certain tensor weight. And if we listen to all of them and have their spectrum, that may be enough. That would be enough to capture all of the in 2 dimensions, though, curvature is scalar. For 2-dimensional manifolds, curvature is essentially scalar. The tensors simplify to that extent. I think let's wrap it up and see you again on Friday.